In this video, we are going to take the Laplace inverse of a function involving an exponential function, right? So the function in terms of s involving an exponential function. This is quite strange, right? So how do you take the Laplace inverse of something like this? So if you can recall the definition of the Laplace transform of the unit step function. So Laplace transform of the unit step function, that is u of t minus a, just a plain one. This one is e to the negative as all over s. This one I've done this one in my videos. And the Laplace transform of the Heaviside function, which is the unit step function multiplied by the function f of t minus a. This is equal to e to the negative as, and this is multiplied by capital F of s. So the Laplace transforms of unit step functions involve the exponential functions in terms of s. So that means that if we are taking the Laplace inverse of something like this, Laplace inverse of e to the negative as multiplied by f of s, right? This one is going to yield the Heaviside function, that is u of t minus a multiplied by f of t minus a. Right, so if you are taking the Laplace transform of an exponential function involving an exponential function, it means we are going to get the unit step function multiplied by a certain function but shifted by a. So the natural thing that comes to our mind if we want to take the Laplace transform of this Laplace inverse, I beg your pardon, so the Laplace inverse of an exponential function multiplied by a certain function, here our function here is 2 over s to the third. So the natural thing that will come to our mind is that we are going to get a unit step function multiplied by a certain function shifted by a. So here the unit step function is going to be u of t minus a, but a in this case is the constant in the exponential function. So the constant in the exponential function in our case here is 4. So right, so here we are going to get u of t minus 4. Right, and this is multiplied by f of t minus 4. So we don't know what f of t minus 4 is. So if we can find f of t, then we can just shift the variable t by 4. So now the task now is to find what f of t is. If I find f of t, I can find f of t minus 4. So how do you find f of t? So f of t, remember, f of t is going to be the Laplace inverse, right, of the remaining function in what we are asked to find. So the remaining function here is 2 over s to the third. So how do you find the Laplace inverse of 2 over s to the third? We know that the Laplace transform, right? So we know that the Laplace transform of a function t squared, this one is going to be equal to 2 over s to the third. Right, so in that case the Laplace inverse of this one is going to return t squared. So this one, the Laplace inverse of 2 over s to the third, that is going to return t squared, like this. So this means that the Laplace inverse of 2 over s to the third, this is equal to t squared. Right, so just like going back, doing the reverse. So let me clean this one. This one was just for the purpose of illustration. Okay, cool. So now we have f of t to be t squared. Now we can find f of t minus 4. This one should be in yellow. I'm sorry for this. So f of t minus 4, this one is equal to t squared. Now we are shifting that by 4. So that is going to be t minus 4 all squared. Now that we have gotten f of t minus 4, we can plug it back here. That means the Laplace inverse of 2 e to the negative 4s all over s to the third. This one is equal to u t minus 4 multiplied by t minus 4 all squared, like this. So this one is the Laplace, is the function in which the Laplace transform is this. So the Laplace inverse of this guy is equal to this Heaviside function. Cool. Now let's look at the second one. Second one, let me do that in blue. So the second one, we are going to get this. How do you find the Laplace inverse of something like this? That is e to the negative 2s divided by s squared plus 9, like this. This one is very easy. So we are coming back here. This one is very important in our video. So it means because we have this exponential function e to the negative 2s, that means we are going to get a unit step function multiplied by a certain function shifted by the constant a. So what we are going to do here is we are going to write a unit step function. So the unit step function here is going to be u of t minus a. But what is a in this case? A is always the constant in the exponential function. So the constant there is 2. We are going to multiply it by a function f of t but shifted by the constant 2. So we are going to multiply it by f of t minus 2. So a in this case is 2, right? So the task now is to find the function f of t. If we can find the function f of t, then we can shift the variable t by 2, and that will be the function ft minus 2. Cool. So now let's do that. So the function f of t is the Laplace inverse of the remaining function. The remaining function in this case is 1 all over s squared plus 9. This is very easy. Right, and this one is the Laplace inverse of 1 all over s squared plus 9. It can be written as 3 squared. So this one looks like the what do you call it? The sine, right? Sine of 80. So if you have the Laplace transform of sine of 80, this one is equal to a all over a squared plus s squared. S squared or a squared is the same thing. So let me be consistent. So this one is going to be s squared plus a squared. Right. So that means that the Laplace inverse of a squared, a all over s squared plus a squared, this one is going to return the sine of 80 like this. Cool. So we have something that looks like the sine of 80. What we don't have is this 3. The 3 is not on top here because you have 3 squared at the bottom here. There's supposed to be 3 on top. So there's no cause for alarm. What I can do is to just remove the 1 and then put 3. But I have to take it away by dividing the Laplace inverse by 3, right? So this 3 is going to cancel this 3 and the function is preserved. Now I have 3 on top here and then 3 squared at the bottom, and that is like sine of 3t, looking at what we have here. So that means that f of t, so f of t in this case is 1/3, and the Laplace inverse of this one is going to be sine of 3t. So that's going to be sine of 3t. So this is our f of t, but we need f of t minus 2 because we have to shift the function by 2, the constant in the exponential function. This is what we have here. So remember to always shift the function. So f of t minus 2, this is going to be 1 over 3, and then sine of 3 into shift t by 2 like this. So this is f of t minus 2. So we can now go back here and wrap up our integral. Our Laplace inverse question. So the Laplace inverse of e to the negative 2s divided by s squared plus 9. This one is equal to u of t minus 2 multiplied by 1/3. So let me bring the 1/3 here, why not? And then sine of 3 into t minus 2 like this. And this one is the Laplace inverse of this function. All right, this is very easy. So now let's go to the third one. So the third one, I'm going to do it in green. So the third one, we have this. We want to find the Laplace inverse of this function, and the function is s e to the negative 3s divided by s squared plus 4. Right. So using this one again, we are coming back here to the Laplace inverse of something involving an exponential function. That is going to be the unit step function u of t minus a. So let's write that. So this one is going to be u of t minus a. What is a in this case? A is the constant in the exponential function. So that is going to be 3. And then I'm going to multiply it by f of t minus a. So f of t minus a, like what we have here. But a in this case is 3, the constant in the exponential function. So we have to find f of t and then shift the variable t by 3. So now let's find f of t. Now you know that f of t is the Laplace inverse of the rest of the function. So f of t is the Laplace inverse of the rest of the function. The rest of the function is s all over s squared plus 4. The exponential function is only there to make us realize that we are having a unit step function. So the rest of the function is now s over s squared plus 4. So now how do you take the Laplace inverse of this? We can go back here again, but this one can be written as the Laplace inverse of s divided by s squared plus 4 can be written as 2 squared, like this. So when we come back here, that means that the Laplace inverse, I didn't write it, so this one is like the cosine, right? So if you have the Laplace transform of the cosine of at, this is equal to s divided by s squared plus a squared. In that case, the Laplace inverse, so the Laplace inverse of s over s squared plus a squared, this one is going to return the function that's cosine of at, like this. Cool. So now this one is just similar to this. Therefore, the function f of t is going to be equal to, this one is the cosine of a, in this case is 2, so it's going to be at 2t, like this. So now we have f of t, we can find f of t minus 2 because we have to shift it. F of t minus 3, I'm sorry, the constant in the exponential function. So f of t minus 3 is going to be cosine of 2 multiplied by t minus 3. Just shift t by 3 and that should be it. So in that case, the Laplace inverse of s multiplied by e to the negative 3s divided by s squared plus 4, this one is equal to the unit step function, that is u of t minus 3 multiplied by f of t minus 3, and f of t minus 3 is cosine of 2 into t minus 3, like this. And this one is the answer to the Laplace inverse of this function. Alright, so now let's go to the fourth one, right? So the fourth one, I'm going to do it in white pen, why not? So the fourth one, we are going to get the Laplace inverse of this. So how do you find the Laplace inverse of this? The Laplace inverse of 3, this one is going to be s plus 1 multiplied by e to the negative 4s. This is divided by s plus 1, right? S plus 1 squared and then plus 9. How do you take the Laplace inverse of this? Remember, this one is equal to the unit step function, that is u of t minus a. What is a in this case? So a is always the constant in the exponential function. So a is the constant in the exponential function. So when we go to question 4, the constant in the exponential function is going to be 4. There are a lot of constants here, so we have 9 and 1, but we have to know which constant to use. It's always the constant in the exponential function, so which is u of t minus 4. Then this is multiplied by f of t minus 4. So now we don't know this, we have to find f of t and then replace t with t minus 4. So now f of t is the Laplace inverse. F of t is the Laplace inverse of the remaining function. What is remaining? That is s plus 1 divided by s plus 1 all squared plus 9 can be written as 3 squared, like this. Cool. So this one is like applying the first shifting theorem of the Laplace transform. That is like shifting the variable s by -1. So if you can recall, the Laplace transform, right, of this one is like the cosine of something. Cosine because we have s on top here, right? So this one is going to be the cosine of, let's say 80, right? But then this one is going to be shifted by a certain variable, a certain number. Let's say this one is going to be bt, like this. This one, the Laplace transform of this one is going to be, you are going to have the cosine of at, all right. So that is going to be s all over s squared plus 1, right? So it's going to be s squared plus a squared. That is what we have here. But we are going to shift the s variable by b here. So if I can put negative b here, that is going to be, we are going to shift the s variable by negative b. So that is going to be, in place of s, we are going to shift it by negative b. So s minus negative b. And this one was s squared, so it's going to be s minus negative b and all this one squared. So the Laplace transform of something like this is going to be equal to s plus b divided by s plus b all squared plus a squared. So in that case, if you are taking the Laplace inverse of this, so that means that the Laplace inverse of this one is going to be what? So the Laplace inverse of something like this one is going to yield e to the negative bt multiplied by cosine of at. So this is what we have here. So we have to find the Laplace inverse of something like this. So with this one, applying the first shifting theorem of the Laplace transform, f of t here can be written as this. So this is cosine, but cosine of what? So it's going to be cosine of something, cosine of 3, because this one is s all over s squared plus 3 squared. So you just pretend the shift does not exist. So this one is going to be cosine of 3t, like this. But the s variable is shifted by -1, so that is going to be e raised to the power -1 times t, like this. So f of t is going to be e to the negative t multiplied by cosine of 3t, like this. Right, so this is what we have. So what about f of t minus 4? So f of t minus 4, replace t with t minus 4. That is going to be e to the negative into t minus 4. And this is multiplied by cosine of 3 into t minus 4, like this. So this is the function f of t minus 4. Now you can go back to question 4. That means the Laplace inverse of s plus 1 multiplied by e to the negative 4s divided by s plus 1 all squared plus 9. This one is equal to u of t minus 4 multiplied by f of t minus 4, which is e to the negative into t minus 4 multiplied by cosine of 3 into t minus 4, like this. So this one is the Laplace inverse of this function. So this one, you just have to apply the first shifting theorem, which is what we have here, and then we just find f of t minus 4 and replace it here, and that should be the Laplace inverse of this guy here. Cool. So now let's go to the fifth one. So the fifth one, I'm running out of colors, so let me do it in this one for the very first time. So the fifth one, why not? I'm going to solve this one, the Laplace inverse. How do you take the Laplace inverse of this? So that is going to be 3 e to the negative 2s. This is divided by s plus 1, s plus 2 squared plus 25. Cool stuff. So this one, straight away, u of t minus a in this case, a is the constant in the exponential function. That is u of t minus a. So this one is going to be u of t minus 2. If we go here, that is from our very first one here. So u of t minus a is the constant in the exponential function. All right, so now this is what we have, and this is going to be multiplied by f of t minus 2. All right, so now how do you find f of t? F of t is the Laplace inverse of the remaining function. The remaining function here is the one without the exponential, and that is going to be 3 divided by s plus 2 all squared plus 25. 25 can be written as 5 squared. So this one is cool, and this one looks like the sine of at multiplied by a shift, multiplied by a certain exponential function. So let me do it here for you to see. So if we have this, the Laplace transform of something like this, e to the negative bt multiplied by sine of at. This one, if you can recall, this one is going to be a divided by s plus b all squared plus a squared. So this one is the Laplace transform of this function. So we are just going to shift the s variable by the constant in the exponential function. So the s variable is only s here, so we are going to shift it by negative b. So s minus negative b, that is s plus b. So that means that if we take the Laplace inverse of this guy here, which is a all over s plus b all squared plus a squared, this one is going to return e to the negative bt multiplied by sine of at, like this. So this one looks like this, right? So now how do you take the Laplace inverse of this? But here this is a and this is a squared, but we don't have that here. This is 3 and this is 5 squared, so there should be 5 here. So permit me, what I'm going to do, I'm going to clean this 3, right? I'm going to bring it here, and then I'm going to introduce 5, but I can't just introduce 5. I have to take it away by dividing by 5. So I can say times 1 over 5, like this. So the 5 will cancel the 5 and the 3 can go inside, and that's like the original function. The function is preserved. So now if we do this, the function f of t is now like this, 3 over 5. Then the Laplace inverse of 5 divided by s plus 2 all squared plus 5 squared. And this one is equal to 3 over 5. Now the Laplace inverse of this is now like this. So this one is going to be e to the negative bt. B is the constant in the exponential function, that is this one, right? So the s here is shifted by 2, so this one is going to be e to the negative 2t, and then this is going to multiply by the sine of at. So the sine of what is a in this case? A in this case is 5, so that is going to be 5t, like this. So this one is the function f of t. We can now find the function f of t minus 4. That is f of t minus 2. I beg your pardon. So f of t minus 2. So the constant in the exponential function here is 2. So this one is going to be 3 over 5 e to the negative 2 into t. So t is now going to be shifted by 2, like this. And then we are going to have sine of 5t, and t is going to be shifted by 2, like this. So this is the function f of t minus 2. So now we can go back to our function. So the Laplace inverse of 3 e to the negative 2s divided by s plus 2 all squared plus 25. This one is equal to u of t minus 2, that is u of t minus 2 multiplied by f of t minus 2, which is 3 over 5, which I'll bring in front here, and then e to the negative 2 into t minus 2 multiplied by sine of 5 into t minus 2, like this. And this one is the Laplace inverse of this function. Alright, cool stuff. So now the last one, this is the very last one, question 6. So question 6, we are asked to find the Laplace inverse of this. So the Laplace inverse of this function. We are asked to find the Laplace inverse of this function. The function is e to the negative s divided by s into s squared. S into s squared plus 4, like this. Cool. So what do you have here? This one is going to be u of t minus a. What is a in this case? A is the constant in the exponential function. In this case, it is 1. So 1s. So 1 and then f of t minus 1, like this. So now we have to find f of t before we can shift it by 1. So f of t is equal to the Laplace inverse of the rest of the function without the exponential function, which is 1 all over s into s squared plus 4. How do we take the Laplace inverse of something like this? Right, so the Laplace inverse of something like this, that means we have to use like partial fractions to break this one down, right? So let me switch colors and deal with this one using the partial fractions. So partial fractions, 1 all over s into s squared plus 4. This is equal to a over s plus, this is bs plus c divided by s squared plus 4. Right, So now let's do cross multiplication. This is a times s squared plus 4, and this is going to be multiplied by s times bs plus c. All this one is divided by s into s squared plus 4, the LCM, and 1 all over s into s squared plus 4. Cool. So now this one, the denominators are the same, so we can multiply both sides by this one, and that will eliminate the denominator. What is left is the numerator, which is 1 equal to foiling, that is going to be as squared plus 4a, right, plus 4a, and then plus and this one is going to be bs squared, and then plus cs, like this. So now we can gather like terms, right? So gathering like terms, you have 1 to be equal to the coefficient of the s squares, that's a plus b, right? We have just cs, and then plus 4a, which is the constant, plus 4 times a. Right, so now we can compare both sides. So the constant here, 4a, is equal to 1. The constant on the left hand side is 1. So that means that we have 4a to be equal to 1. So by comparing both sides, 4a is equal to 1. That means that a is equal to 1 over 4. Cool. So now we have a to be equal to 1 over 4, but c is going to be 0 because the coefficient of s on the left hand side is 0. There is no s term. So that means that c is equal to 0. So and a plus b, this is equal to 0 as well. The coefficient of s squared is 0. So when a plus b is 0 and a is 1 over 4, that implies that b is equal to negative 1 over 4 because the two must sum to 0. Now that we have a, b, and c, we can go back to our equation and then we can just plot them in. So let me do it here. So 1 all over s into s squared plus 4. This one is equal to a. A is what exactly? 1 over 4. So that is going to be 1 over 4 times 1 over s, like this, plus bs plus c. B is negative 1 over 4. So that is going to be, let me just cancel this one, put negative 1 over 4 multiplied by s over s squared plus 4. And then plus c. C is 0, so there's no effect. 0 over s squared plus 4 is 0. And then this is what we have. So that means that this 1 over s into s squared plus 4, this one is equal to 1 over 4 outside. Then you are going to have 1 over s minus s all over s squared plus 4 can be written as 2 squared, like this. Cool. So now we are ready to take our Laplace inverse. So one cool thing about the Laplace inverse is that we have to know the tricks of doing partial fractions. So the Laplace inverse of our function, the f of t, so f of t is the Laplace inverse of the remaining function. That is the Laplace inverse of this, which is the same as this, and this is equal to that. So I'm just going to take the Laplace inverse of this function. That is going to be 1/4 is a constant. Then I'm going to have the Laplace inverse of 1 over s minus s over s squared plus 2 squared. Cool. So f of t is going to be 1 over 4, and then the Laplace inverse of 1 over s. All this one is multiplied by 1 over 4 in front, minus the Laplace inverse of s all over s squared plus 2 squared, like this. And all this is multiplied by 1 over 4. So Laplace inverse of 1 over 4 is what? 1. Because the Laplace transform of 1 is 1 over s. The Laplace inverse of 1 over s is 1. Minus the Laplace inverse of s over s squared plus 2 squared. This one is going to be cosine of the constant times t. The constant here is 2 times t, like this. So this is what we have for the Laplace inverse of our remaining function, which is this one. Now that we have f of t, we can find f of t minus 1 and then plug it back into our equation. So f of t minus 1, just shift t by 1. So 1 over 4, 1 is a constant, there's no shift. And then we are going to have the cosine of 2 times t. T is now going to be shifted by 1, like this. So now that we have f of t minus 1, we can come back here and then replace it. So this one is going to be equal to u of t minus 1 and multiply by f of t minus 1, which is 1/4. The 1/4, I am going to multiply it here, and then I'm going to have 1 minus cosine of 2 into t minus 1, like this, and close this. We have 3 parentheses. All right, cool, that's it. And this one is the Laplace inverse of this function. All right, cool. So that is how to solve the Laplace inverse of our exponential functions. Like if you have an exponential function in terms of s, so what should come to your mind is the unit step function. Just write the unit step function, which is u of t minus the constant in the exponential function. Then you take the Laplace inverse of the remaining function. After that, you shift it by the constant in the exponential function and you multiply. And that should be how to solve the Laplace inverse of functions involving the exponential function. So this is the trick that I used in solving these ones. If you find this video helpful, please give me a thumbs up and subscribe to Calculus Diaries, and I will see you in my next tutorial. Bye bye.